Push a book across a table, you feel friction, resistance. The book slows down. You think surfaces are rubbing against each other, rough edges catching mechanical forces. But that's not what's happening. Not at all. Friction doesn't exist, not the way you think. What you're feeling is electromagnetic repulsion. Billions upon billions of atoms pushing against each other. And here's the thing. They never touch. Not once. You've never touched anything in your entire life. Now that sounds crazy. You're sitting in a chair right now. You can feel it. You're touching it. Right? No. You're hovering above it. Microscopic distance. Angstroms 10 to the minus 10 meters. The electron clouds around the atoms in your body are repelling the electron clouds in the chair. It feels like contact. It feels solid. But it's electromagnetic repulsion. All the way down. Let me tell you what we usually think friction is. You look at surfaces under a microscope. They're rough, jagged little peaks and valleys. When you slide one surface over another, those peaks catch on each other. They resist motion. That's friction. That's the mechanical picture. And it's not completely wrong. Rougher surfaces do have more friction. That part is true. But why? What's actually happening when those peaks catch? The answer is electromagnetic forces. Always. Every time. See, atoms are mostly empty space. The nucleus is tiny 10 to the minus 15 meters. The atom as a whole is about 10 to the minus 10 meters. That's 100,000 times bigger. So the atom is almost entirely the electron cloud. The region where electrons exist, where they have probability of being found. And electron clouds repel each other. Why? Because electrons have negative charge. Like charges repel electromagnetism. But there's more to it. There's also the Pauli Exclusion Principle. Wolfgang Pauli figured this out. No two electrons can be in the same quantum state. If you try to push electron clouds together, you're trying to put electrons in the same place with the same state. The universe says no. The resistance you feel, the force pushing back, that's the exclusion principle enforcing itself through electromagnetic interaction. So when you push that book across the table, what's really happening? The atoms on the bottom of the book, their electron clouds, are getting close to the atoms on the table surface. The electron clouds repel. They push back. If the surfaces were perfectly smooth and you pushed gently, the book would slide easily. The electron clouds would repel uniformly. Not much resistance. But surfaces aren't perfectly smooth. They have bumps, microscopic mountains, and valleys. When a bump on the book meets a bump on the table, the electron clouds are forced closer together. More repulsion, stronger force. And here's the key thing. The atoms aren't rigid, they're flexible. The electron clouds deform. The nuclei shift position slightly. That deformation takes energy. And when the bump passes and the atoms snap back to their normal shape, that energy gets released, usually as heat. The atoms start vibrating more. Temperature goes up. That's why friction creates heat. It's not rubbing in some mechanical sense. It's constant deformation and relaxation of electron clouds. Electromagnetic energy converting to thermal energy. Richard Feynman talked about this. He said, and I'm paraphrasing, that when you get down to it, friction is just electricity in disguise. It's electromagnetic forces between atoms. There's no separate friction force that's fundamentally different from electromagnetic forces. It's all the same thing. Now, you might say, all right, but it still slows me down. Whether it's mechanical or electromagnetic, it's still friction, right? Yes. But understanding what it really is changes how you think about it, changes what you can do about it. Let's talk about smooth surfaces. Why do smooth surfaces have less friction? Because there are fewer bumps. The electron clouds can stay farther apart on average, less deformation, less energy lost. If you could make a perfectly smooth surface, atomically flat, and slide it over another perfectly smooth surface, you'd have very little friction. The electron clouds would repel, but uniformly, no catching, no deformation. In practice, perfectly smooth surfaces sometimes stick together because the electron clouds can get close enough that attractive forces start to matter. Van der Waals forces. Still electromagnetic, but attractive at certain distances. That's why gauge blocks, Those precision measuring tools can ring together, you slide them together, and they stick. Not glue, not magnetism, just electromagnetic forces at the atomic level. You can pull gauge blocks apart, but it takes force. The electromagnetic attraction between the surfaces has to be overcome. Machinists use this. They stack gauge blocks to create precise measurement standards. The blocks stick together so well you can lift the whole stack by picking up just the top block. That's electromagnetism. The same force that creates friction can also create adhesion, depending on the geometry, the distance, the materials involved. Now let's talk about lubricants. Why do they work? You put oil between two surfaces, a thin layer of molecules. Now when the surfaces move, the oil molecules slide past each other instead of the surfaces directly interacting. But what does slide past each other mean? It means the electron clouds of the oil molecules are repelling each other, but the forces are weaker. The molecules are designed to have smooth electron distributions, less deformation, less friction. The oil isn't magic. It's just providing a layer where electromagnetic interactions are weaker and more uniform. Some lubricants work even better. Graphite, for example. The carbon atoms in graphite form sheets. The sheets are held together by weak forces. They slide over each other easily. The electron clouds repel, but gently, low friction. That's why pencils work, by the way. The graphite sheets slide off the pencil and stick to the paper. Electromagnetic forces holding them to the paper, but weak forces between the sheets. Molybdenum disulfide works the same way. Layered structure. The layers slide. Space agencies use it to lubricate satellites because it works in vacuum. Regular oil would evaporate in space, but molybdenum disulfide doesn't need to be. Liquid is still electromagnetic, just a different configuration of atoms. Now here's something wild. Superfluids liquid helium at very low temperatures. Helium becomes a superfluid below about 2 Kelvin. And superfluids have zero viscosity, zero internal friction. Why? Quantum mechanics. The helium atoms form a collective quantum state. They all act as one. There's no mechanism for energy dissipation, no resistance. It's still electromagnetic forces. The atoms still repel each other. But the quantum coherence means they move without losing energy. Superfluids can flow up the walls of containers. They can leak through impossibly tiny holes because there's no friction to stop them. That's an extreme case, but it shows you friction isn't inevitable. It depends on the details of how electromagnetic forces play out. Here's another example. Superconductors. In a superconductor, electrons pair up into Cooper pairs. These pairs act like a superfluid. They flow without resistance. Zero electrical friction. Normal conductors have resistance. When electrons flow through a wire, they scatter off atoms. Electromagnetic interactions cause them to change direction, lose energy. That's electrical resistance. It heats up the wire. But in a superconductor, the Cooper pairs move coherently. No scattering, no resistance, no heat. John Bardeen, Leon Cooper, and Robert Schrieffer figured out how this works. BCS theory. The electrons pair up because of interactions with vibrations in the crystal lattice phonons. Sounds complicated, but the key point is the pairing creates a quantum state where electromagnetic interactions don't dissipate energy. Again, it's electromagnetic forces, but arranged in a way that eliminates friction. So friction isn't some fundamental force of nature that's separate from everything else. It's a consequence of electromagnetic interactions. And it can be reduced, even eliminated, if you set things up right. Now let me tell you something that might bother you. Without electromagnetic forces, there would be no friction. You're thinking, great, that sounds good. No friction, no resistance. But also, you'd fall through the floor. The floor holds you up because of electromagnetic repulsion. The atoms in your feet repel the atoms in the floor. That's what stops you from falling through. If you turned off electromagnetism, you'd pass right through. You, the floor, the earth, all just ghosting through each other. Only gravity would matter, and you'd fall to the center of the earth. So friction is annoying, but it's also necessary. It's the same force that makes matter solid, that lets you stand, walk, pick things up. You never touch anything. That's true. Your hand hovering a tiny distance above this book. But the electromagnetic repulsion is so strong, it feels like solid contact. The force is real. The effect is real. The sensation is real. But the contact, that's an illusion. Let me give you another way to think about it. When you walk, you push backward on the ground. Friction between your foot and the ground stops your foot from sliding. And by Newton's third law, the ground pushes you forward. That's the mechanical description. And it works. It predicts what happens. But what's really going on? Your foot's atoms repel the ground's atoms electromagnetically. You push back. The ground pushes forward. Electromagnetic forces. When you brake in a car, the brake pads press against the rotors. Friction slows the car. But really, electron clouds in the brake pad repel electron clouds in the rotor. The car's kinetic energy converts to heat through electromagnetic interactions. The brake pads get hot. Sometimes red hot. If you're braking hard down a mountain, that's electromagnetic energy becoming thermal energy. The atoms in the brake pad vibrating faster and faster. When you write with a pen, ink molecules stick to paper through electromagnetic forces. Van der Waals forces, specifically weak, but enough to leave a mark. Every physical interaction you've ever experienced is electromagnetic or gravitational, but gravity is way weaker. For everyday stuff, it's electromagnetism. The strong nuclear force holds atomic nuclei together, but it doesn't reach beyond the nucleus. You never feel it directly. The weak nuclear force causes radioactive decay. But again, not something you interact with directly. Electromagnetism runs the show. Friction, tension, compression, elasticity, stickiness, all electromagnetic. Now, there's something interesting about the direction of friction. Friction always opposes motion. If you're sliding left, friction points right. If you're moving right, friction points left. Why? Because the electromagnetic interactions are dissipating energy. They're converting kinetic energy to heat. And the way to dissipate energy is to oppose motion. It's not that the atoms know which way you're moving and decide to push back. It's that the statistical average of all those electromagnetic interactions creates a net force opposing motion. Think of it like this. When you slide a book, the atoms at the interface are being pushed into configurations they don't want to be in. Higher energy configurations. They resist, they push back. And when they relax, they vibrate. That's heat. The direction of the resistance is automatically opposite your motion. That's just how the geometry works out. Here's another weird thing. Static friction versus kinetic friction. Static friction is when something isn't moving yet. Kinetic friction is when it's already sliding. Static friction is usually stronger. It takes more force to start something moving than to keep it moving. Why? Because when objects are sitting still, the atoms have time to settle into low energy configurations. Little electromagnetic bonds form Van der Waals forces, maybe even chemical bonds if you wait long enough. To start moving, you have to break those bonds. That takes extra force. Once you're moving, the atoms don't have time to settle. You're constantly breaking and forming new interactions. Less resistance. That's why it's hard to push a heavy box at first, but easier once it's sliding. You're overcoming static friction to get started, then fighting kinetic friction to keep going. All electromagnetic. All the time. You know, some materials have very low friction. Teflon, for example. Non-stick coating on pans. Why is Teflon slippery? Because it's made of carbon and fluorine atoms, fluorine holds its electrons very tightly. The electron cloud is compact, uniform, not much stickiness. When you try to slide something on Teflon, the electromagnetic interactions are weak. The electron clouds repel, but there's not much deformation, low friction. Ice is slippery for a different reason. When you press on ice, you melt a thin layer at the surface. The pressure and friction create a tiny amount of liquid water. You're not sliding on ice, you're sliding on water. And water molecules slide past each other more easily than ice crystals. Lower friction. Again, all electromagnetic. The hydrogen bonds between water molecules are weaker in the liquid than in the solid. Actually, Ice is interesting. For a long time, people thought pressure alone melted the surface. But that's not quite right. It's a combination of pressure and friction. The friction creates heat, and the pressure lowers the melting point slightly. Together, they create that thin water layer. Skaters know this. The blade of a skate is thin, high pressure. Plus, the motion creates friction, creates heat. The ice surface melts. You glide on water. Same thing with sledding. Same thing with curling, that sport where they slide stones across ice. All electromagnetic interactions creating just enough heat to melt a microscopic layer. Let me tell you something about friction at the quantum level. When atoms get very close, their electron clouds overlap. Not completely, but enough that quantum effects matter. The electrons start to feel each other's wave functions. The probability distributions interact. This is where the Pauli Exclusion Principle really kicks in. The electrons can't be in the same state, so the system's energy goes up dramatically. That increase in energy is the repulsion. It's not just like charges repelling. It's the quantum mechanics of identical fermions. And it's incredibly strong. This is why matter is solid. Why you can't push your hand through a table? The exclusion principle creates a wall of electromagnetic repulsion. Friction is just that wall, but tilted. Instead of pure repulsion, there's also a component opposing motion. Here's something Feynman emphasized. All the different forces we experience in everyday life, they're not really different. Friction, tension in a rope, compression in a spring, the feeling of hardness when you press on something, all electromagnetic. We give them different names because they feel different, because they occur in different contexts. But fundamentally, they're the same force. The electromagnetic force between charged particles, electrons and protons, attracting and repelling. That's it. That's all you need to explain every tactile sensation you've ever had, except gravity. Gravity is different, but gravity is weak. You only notice it because the Earth is huge. For interactions between objects on human scales, gravity is negligible compared to electromagnetism. If you and I stand next to each other, the gravitational attraction between us is about 10 to the minus 8th newtons. Completely negligible. You'll never feel it. But the electromagnetic forces between the atoms in our bodies and the ground, enough to hold us up against the entire mass of the Earth pulling down. Electromagnetism is stronger than gravity by about 40 orders of magnitude, a 1 with 40 zeros after it. Incomprehensibly stronger. So when you feel friction, when you feel resistance, what you're really feeling is the collective electromagnetic push of billions of atoms. Each individual atom pushes with a tiny force. But there are so many of them. The force adds up. It becomes significant, strong enough to stop a car, strong enough to let you walk. And not one of those atoms touches another. They hover, they repel. They exchange virtual photons, if you want to think about it in quantum field theory terms. But they never touch. Contact is an illusion, a useful illusion, a persistent illusion, but an illusion nonetheless. You are hovering above your chair right now. The distance is so small you could never measure it directly, but it's there. Your feet hover above the ground. Your hand hovers above this table. There is always a gap, always a tiny space where electromagnetic forces do their work. That's the reality. That's what friction is. That's what touching is. When you clap your hands together, you're not actually making contact. You're compressing the electron clouds. The atoms get closer. The repulsion gets stronger, and you feel resistance. The sound of the clap, that's air molecules being pushed out of the way by the electromagnetic shock wave of your hands coming together. The heat you feel if you rub your hands together, that's electromagnetic energy converting to kinetic energy of atoms. Vibrations, temperature. Every sensation is electromagnetic. Now, does knowing this change anything? Does it matter that friction is really electromagnetic repulsion? In some ways, no. The equations work the same. You can calculate friction forces, predict motion, design machines. The labels don't matter. But in other ways, yes. Because understanding the real mechanism opens up possibilities. If friction is electromagnetic, maybe you can control it with electromagnetic fields. Maybe you can design surfaces at the atomic level to minimize it. Maybe you can exploit quantum effects to eliminate it entirely. That's what superconductors do. That's what superfluids do. They take advantage of the quantum nature of electromagnetic interactions to achieve zero resistance. And maybe there are other tricks we haven't discovered yet. Other ways to manipulate atoms and electrons to reduce friction. Nanotechnology is exploring this. Carbon nanotubes, for example. Incredibly smooth at the atomic level. Very low friction. You could use them as bearings in tiny machines. Graphene, single layers of carbon atoms, also has interesting friction properties. The atoms are all in one plane. Very uniform, controllable. That's the power of understanding what's really going on. Not just describing the effect, but knowing the cause. Friction is electromagnetic repulsion. That's the truth. That's the reality. And you've never touched anything in your life. When you push a book across a table, you're forcing billions of electron clouds to repel each other violently. Constantly. Deforming and relaxing millions of times per second. When you brake a car, you're manipulating electromagnetic fields. Converting kinetic energy to heat through atomic scale interactions. When you walk, you're surfing on a wave of electromagnetic repulsion. Your feet never touch the ground, but the forces are real enough to push you forward. That's roughly where we are. Friction isn't a separate mysterious force. It's electromagnetism in action. The same force that holds atoms together, that makes chemistry possible, that lets light interact with matter, it's all connected. All the same thing, just different manifestations. The universe is simpler than it looks, fewer fundamental forces. More electromagnetic interactions than you ever imagined. And the illusion of contact, that's just your brain interpreting electromagnetic repulsion as solidity, as touch, as friction. But now you know. Now you can't unknow it. Every time you feel friction, you'll remember. Electron clouds, Pauli exclusion, electromagnetic forces. You're never touching anything. You're just very, very close. Interesting, isn't it?